Okay, we're going to talk here about what we kind of see in the Khan Academy video, where they're talking about the Rydberg equation and what we get from it, this atomic spectra. What we see here is an atomic emission spectra, different than in absorption spectra. In absorption spectra, this would be kind of a rainbow color going across, and we'd have black lines where the gas kind of ate up the light, the gas ate up the light there. And what we see instead is a excited gas emitting light in this case, for an emission spectra. We talked about this kind of in the previous video as well. This is some hydrogen alpha, right, as the right line. And then we have these three other lines, signaturizing hydrogen. And this was, found at the Rydberg equation, and it was actually found by an individual named Balmer using the Rydberg equation. And for this scenario, what we actually have for hydrogen here is these lines are actually coming down to the n equals 2 position. These lines are coming down like this. And I guess there's a fourth one there, right? In order to create this. But what would happen if you had a scenario where the lines didn't come down to n equals 2? What if you had a scenario where the lines came down to, n equals 1? They went a little further. There's a little bit more energy. In this case, this was actually found. It's the same equation. It's all hydrogen again. We're just going to a different end state for our energy level. This was found by Lyman. Same equation, just bloop, different thing. The reason why Balmer didn't find these is all of this light from the hydrogen alpha band right here in red, and then we kind of got this turquoise and the blue and then the purple. This is all in the visible spectrum. Balmer could actually see this. He could not see what Lyman found. What Lyman found is actually more in the ultraviolet band of light. So it's invisible to the naked eye. It's still light, but you're not going to find it. Beyond that, if we actually say, hey, look, I don't want to go down to n equals 1 and go into the ultraviolet. I want to go the other way, opposite of this, more energetic light. If we go up here into n equals 3 and kind of make all of our band jumps like bloop, bloop, and then, other ones if they existed, and they do. This is actually known as the Paschen series, and I'm missing a C on the Paschen. Ugh, spelling. This is the Paschen series, and this series takes place in the infrared, so it's also invisible to your naked eye, but with detectors we can pick it up. Actually, if you want to see infrared, your cell phone cameras, if you go into your camera mode and you look at your TV remote and you start clicking some buttons, normally you can see a little light flashing there, or if you ever see a security camera, if you hold your cell phone camera up to it, you might see a bunch of like little beads of red in there. A lot of security cams put out infrared so they can see at night. But that's the Paschen series. It's the same thing with the Rydberg equation. It's just ending at a different point. And if you want a quick little note in history and more names to yourself, bloop, 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 you just do the same thing, but you pick n equals, 4, 5, 6. If you went up beyond this, 4 is what's known as the bracket series, 5 is what's known as the fun series, and 6 is Humphrey's series. There's some stuff beyond 6, but at that point, you're literally beating the dead horse right now. We know what you're doing here. It's just Rydberg's equation. Ta-da. The one thing that's kind of a little bit weird about Rydberg's equation and what gave scientists a little bit of a headache is Rydberg's equation works perfectly for atomic hydrogen. But when you look at helium, it just works pretty well. And when you go beyond helium, it completely breaks down. And the reason being is that if you look on an atomic level at the atomic nucleus with all these protons and neutrons here, as you have heavier and heavier elements, which would have more and more electrons, and we'll just kind of draw them in their kind of SPDF orbitals, like 6 of them and then 8, whatever. Because you have more and more of these electrons and you're looking at these outer ones to kind of make the jumps, you get greater and greater shielding on the inside, and this nucleus, as well as the shielding electrons, mess things up for later observations. Things kind of get hocus pocus weird. Things don't work very well for heavier and heavier elements. So we need to find a different way to kind of map those out. But the Rydberg equation and what Bohr kind of theorized from it work very, very well with hydrogen because it is just a proton and it is just an electron doing its thing. We don't have to worry about anything else getting in the way of that. So because of this, it works out very well for Balmer, Lyman, Paschen, and our other scientists there. Even if we can't see what they're doing, we can still detect it with some detectors. So that's a quick little thing there about that. I know the video didn't really talk about it, but I wanted to bring that up so you could see it and understand what's going on there beyond just the standard stuff. Okay? So take it easy. Have a good one.